let's get started. Welcome everyone. I'm Lane Davis. I'm the president of the AELC. And over here is Tom, our treasurer, Rob, our vice president, and James, all the way in the back, is our secretary. So those are the officers. Tonight, since we have an outside speaker, our format changes. I'm just going to go over the club calendar quickly, and then we'll shift into the talk from there. So bear with me. First of all, this coming Saturday, there are two events going on. One of them is there's an open house down at Muddy Run Observatory. How many people know about Muddy Run? Okay, just look it up on the web if you don't know. There'll be a map on there about how to get to it. It's in the, not the far southern end, but the southern end of the county, kind of. About maybe, I don't know, 20 minutes drive south of the city of Lancaster. Excellent facility. If the weather's decent, which, you know, it's too soon to tell, worth going there. You're going to get much darker skies than you get here. The other thing that's going on this coming Saturday and Sunday is the Northeast Astronomy Forum. How many people know about that? Okay. How many people have been to that? Very good. Okay. That's running over the weekend. Saturday looks like the better day weather-wise so far. And they'll have outdoor solar observing, and you get a chance to see some of the best solar filters, by the way. I mean, the kind of things that cost as much as your car. So there that you can look at. Unfortunately, there's not a lot of activity on the sun. You take what you can get. And they have good lectures there. Plus, they have a whole gymnasium full of equipment, which we all love. All right. Next thing will be Saturday the 13th of April, Planetarium Open House at Manheim Township High School. Okay, and that's just down 501 here. You can look it up on the web. I think this one starts at, oh, this is on our website, by the way. Starts at 7 p.m. So that will be well worth it. And they'll bring out telescopes also if the sky is clear. And then finally, Friday, April 26th, Stars Over the Susquehanna. This is one of the star watches that we conduct ourselves. It'll be at the Columbia Crossing Visitor Center, just right along the river, just south of Columbia, the city of Columbia. Unfortunately, the light pollution there is just about as bad as you can imagine, but we'll still have scopes there that you can look through, plus a talk inside. And that one starts. Hang on. The talks start at 7:30. We start trying to look at things in the sky at 8:30. Any questions about any of that? Okay. Our speaker for the evening.
Oh, wait, I just wanted to add a couple.
I'm sorry. Go ahead.
Quickly. The Spring Star Party, just, gosh, was that last week now? We had about 100 people at Peckler Valley come and see a planetarium show and look through some telescopes from Lane and Shirley and George. And I thought it went really well. I thought it was good. The night sky was probably the best we've had there. And it turned out really well. For those of you who want to, you guys know it's 50 years of something special this July? What is it? Moon landing. Yeah. Right. So what I'm doing is, there was a show made by one of my colleagues down in the Midwest, some state in the Midwest, I don't really know much about the states in the Midwest, I guess, but just fly over on that. So on April 17th, that's in 2 weeks, April 17th, they made a show called Apollo 11, Man's First Step Onto the Moon. It's about a 25-minute show. It was made by a teacher and some students, and it's part of a fundraiser that I'm trying to do for the planetarium and our astronomy club to be able to do more and more programming. It's like $5 a ticket, but on Apollo, or not Apollo 17, on April 17th, you can show up. There are shows at 6 and 6:30. So I will be sending out information for this, but tickets are $5. You can reserve them online and pay online and all that. So April 17th. Also, if you're paying attention to NASA, there's a rocket launch that day. Another Antares rocket, like the one I presented about a couple times ago, is going up on April 17th. And starting at 4:30, I'm going to do my Rockets at Wallops presentation, but in the full dome. So if you want to come and see that, plus the Apollo 11 show, that's at 4:30. So I'll be sending more information about that, but you can get that on your calendar. And lastly, May the 4th, that's Saturday, we're having Dome Fest, which is when my students are doing their presentations. They made shows this year. So I would love for all of you to come out and just enjoy it, or if you have telescopes, we are in want of telescopes at night for some observing as well. I'll send out more information about that, but we could put it on your calendar already. So, any questions? Yeah?
The rocket launch, what time?
I believe that it's scheduled for 4:50, so that's why I'm starting the show at 4:30 on April 17th.
Well, we won't be able to see it then, will
We won't be able to see it visually, but I'll be playing a NASA feed up on the dome at that point. Assuming it works. I assume it's going to work.
It'll work, it's just when.
Yeah, right? Thank you.
Okay, our speaker for the night was here earlier in the year on a different subject. Bob Nye is a freelance writer based in Hummelstown, so he's local. Served as editor-in-chief of Sky and Telescope magazine, which is impressive, from 2008 to 2014. He has a master's degree in science journalism from Boston University, and later worked on the editorial staffs of Discover and Astronomy magazines. He also served as editor-in-chief of Mercury magazine, which is published by the Astronomical Society of the Pacific. He's been a senior editor at Sky and Telescope also between 2003 and 2007. Moved to NASA's Goddard Flight. I'm going to slow down. NASA's Goddard Space Flight Center to work as senior science writer for the Astrophysics Science Division. So, we're lucky to have him. And Bob, the floor is yours.
Thank you. Slide. And I assume everybody can hear me okay without a microphone. I've been told before that I have a loud voice, so maybe it's better I don't have a microphone. And I realized earlier today I actually have another personal connection with Lidditz. Lane mentioned a minute ago that I used to be the editor of Mercury magazine, which is published by the Astronomical Society of the Pacific. The guy who hired me for that position is a guy named James White, who goes by J White. Well, a few years ago, he was the director in Lidditz here at the Linden Hall School. He then left. I'm not sure where he is, but right before I checked my email and I said, I'm giving a talk in Lidditz tonight, and I got an email from him, but I haven't read it yet. But he obviously lived here in Lidditz. Now, this is the first time I've given this particular talk. So I'm going to set my timer on my iPhone for 45 minutes, and if I haven't finished the talk at 45 minutes, I'll then wrap it up quickly in 5 minutes and then take questions. So I just want to thank Lane for inviting me to speak tonight. I want to thank the club. By the way, I love the logo for your club here. It's a really great logo. I want to thank the library for hosting this event, and most of all, I want to thank all of you for coming. So this talk is loosely based on an article I wrote for Astronomy magazine. I actually submitted the article maybe about a month or two ago, then they edited it, and it's going to be in the upcoming issue, the June issue. If you subscribe, you'll get it in late April, a couple weeks from now. Do any of you subscribe to Astronomy? Okay, we have a couple here. So you'll be able to read the article in just a few weeks. And if you don't subscribe but are interested in reading it, this issue will appear on newsstands in early May. So I just, even though I work for Sky and Telescope, I work for both Astronomy and Sky and Tel, and I actually write for both magazines. I had a big feature article just a few months ago in Sky and Telescope about gravitational waves. So this is just, by the way, the opening spread for the article, and you can see my byline right here. So that's just what the opening 2 pages looks like. So what this talk is going to be, the article is mostly about kind of modern stuff, but I thought I don't know what popular audiences know about cosmology, so I'm really going to just try to give a whirlwind tour of the history and current state of the field. And I'll try to make this as non-technical as possible, because believe me, this is really, a lot of this is really, really complicated. So I'm going to try to just hit the highlights, give you kind of the very basics of what you need to know. And if you have any further questions or want me to give more detail on something I spoke about, I'll be happy to take questions at the end. So I'm going to start off in the early 1900s. At that time, most astronomers just assumed that the universe was our galaxy, the Milky Way galaxy. And of course, at that time, they had no idea that it was a spiral shape, that we were like halfway between the center and the edge of the disk. I mean, really at that time, they really didn't know anything about cosmology. They didn't, they just assumed the universe was static, that it wasn't expanding or contracting. I say here in reality, they knew nothing about the size and origin of the universe. You could even argue they knew less than nothing, because what they thought they knew was clearly, we now know today, is wrong. And this was really before astrophysics had been developed, where you start looking at stars and planets and the universe as physical objects that apply, where you can apply the laws of physics. So if you go to the early 1900s, this is still kind of early in the era of astronomical photography, they had low-resolution photos, by modern standards at least, of these spiral-shaped objects that they called spiral nebulae. And then the question is, what the heck were these things? Some astronomers thought they were, solar systems or planetary systems in the process of formation. They didn't know how far away they were. And at the time, if you go back to 1900, they really didn't even have an obvious way of finding out. Okay, the first real advance in cosmology was in the 19-teens. There was an astronomer named Vesto Slipher at Lowell Observatory, and he started to use very crude the spectrograph that existed at the time, and he noticed that the fainter spiral nebulae, when he took the spectrum, the light was shifted toward the red end of the spectrum. So like a Doppler effect, it implied they're moving away from Earth. And he noticed that the fainter the spiral nebulae, the faster they were moving away from Earth. Now, nobody really knew it or interpreted it this way at the time, but we now know that this was actually a very profound result, because this was the first hint that the universe is expanding and getting bigger and bigger. But, as I say here, this idea was really too far ahead of its time. Astronomers had not even established yet that these spiral nebulae were separate island universes way beyond our own Milky Way galaxy. Although, to be fair, there were some astronomers that suspected that was indeed the case, and looking back on their arguments, one of the most famous was an American astronomer named A. Bear Curtis. They were right. They were remarkably prescient, but they didn't really have a way of proving that these were island universes. Okay, then in the late 19-teens, Albert Einstein, without even really realizing the full significance of his own theory, provided a theoretical foundation for modern cosmology, one that we still use today, when he published his general theory of relativity, which is basically a theory of gravity and how space-time, how massive objects cause gravity by bending space-time. Now, if you look at his equations, and he actually understood this, his equations went against the idea at the time of a static universe. His equations showed that one of two things were happening. Either the universe was expanding or contracting, but he didn't believe his own idea, so he introduced this idea that he called a cosmological constant. This would be this pressure exerted from the energy that's existed or latent in empty space, and he thought that this cosmological constant was preventing the universe from contracting and collapsing upon itself. So he was just trying to preserve a static universe. Now later, when it was proven that the universe is expanding, he called his cosmological constant idea his greatest scientific blunder. But as I'll discuss near the end of the talk, this idea has been revived, and it might be one of his most brilliant insights. And then another thing going on in the early 1900s, and this one is another piece of work that was not fully appreciated at the time how significant this was. A very brilliant Harvard University astronomer named Henrietta Leavitt, she was looking at these variable stars, a very specific class called Cepheid variable stars. And here's a plot she made of Cepheid variables in a neighboring galaxy, although they didn't know it was a neighboring galaxy at the time, called the Small Magellanic Cloud, or SMC. And she noticed this very tight relation where the more luminous the star, the longer its pulsation period. So if you knew the absolute luminosity of a Cepheid variable, you then could just tell from the inverse square law where an object gets dimmer with the inverse square of its distance. You could then calculate its actual luminosity, and then you could look at Cepheids at various distances, watch them brighten and fade, and you could measure distances across immense distances using this method. So unfortunately, she died, I can't remember, it was either the late 19-teens or early 1920s. So she did this brilliant work, but she didn't live long enough to really see it applied in a very powerful way. And here, this is just an example. You see this light curve of how a Cepheid will get brighter and fade. And the brighter the more luminous the Cepheid, the longer the period between its peaks. And if you're curious, you can easily find a Cepheid variable is Polaris. The North Star is actually a Cepheid variable. So the next big leap in cosmology came in 1924-25, when I'm sure you've all heard of Edwin Hubble, for whom the Hubble Space Telescope is named. He took Henrietta Leavitt's technique, and once again, she didn't live long enough, and when she died, they hadn't, these new telescopes being put on Mount Wilson were just getting going, so she never had the opportunity to do this work herself, which is a real tragedy. But Hubble took up this project, and he observed 12 Cepheid variable stars brighten and fade in the Andromeda Galaxy, and 22 more in the galaxy M33. So he was able to prove by measuring their period luminosity and how they rose and faded in brightness, that told him the luminosity. He was able to prove that M31 and M33 are vast collections of stars far beyond our Milky Way galaxy. And at the time, most astronomers, to their credit, quickly accepted his results. And this was a monumental breakthrough in cosmology. I mean, this is certainly, I think, one of the top 10 greatest discoveries in scientific history, or in astronomy, if not in science. Absolutely monumental breakthrough. Here we see one of his pictures. You can see right there is a Cepheid variable. Now, his distances he measured were about 1 million light years. We now know it's 2.4 and 2.7 million light years. He didn't realize there are two kinds of Cepheids. but he was correct in his general conclusion, and this forced astronomers to realize that the universe goes way beyond our own Milky Way galaxy, that it's mind-boggling in extent. And they knew there were spiral nebulae that were much farther away. So they knew immediately you go from a universe that's maybe a few 100,000 light years across to now we're talking hundreds of millions or even billions of light years across. So this was, you know, I almost wish I could go back in time to the early 20s, like what a mind-boggling breakthrough that must have been, you know, to suddenly realize that what we thought was the universe was tiny compared to the reality. And then in the mid and late 1920s, and this guy did not get, and you'll hear more of this in a few minutes, this guy did not get the credit he deserved in his lifetime, because once again his ideas were too far ahead of their time. There was a Belgian physicist and Jesuit priest named Georges Lemaitre. I don't know if I'm pronouncing that quite right. But he argued that the recession of galaxies that Vesto Slipher had observed earlier was due to an expanding universe. So he was really the first one to interpret Vesto Slipher's data as an expanding universe. He also calculated the expansion rate. He was off by quite a bit, but he was the first astronomer or scientist to attempt to do this. And I'll talk about this much later, called the Hubble constant. And most of all, he was the first to propose what we now call the Big Bang theory, that the universe arose from what we now call the Big Bang. He called it the primeval atom. So these were all basically correct, brilliant ideas ahead of their time. Okay, now I mentioned Edwin Hubble a couple minutes ago. Most scientists would be very happy to make one great discovery in their lifetime. Well, Hubble made two, and the second one in some ways was even more profound, although he had to make the first discovery before he could make the second discovery. Working with another astronomer at the Mount Wilson Observatory named Milton Humason, now that we knew that these spiral nebulae were distant galaxies, he was able to show in this very crude plot here that the more distant the galaxy, the faster it's moving away from us. This is the expanding universe. What's really interesting is that Hubble was an observer. He had a fundamental mistrust of theory, and he lived into the mid-1950s. He never fully accepted the idea that this data that he collected with Milton Humason was showing an expanding universe. And by the way, I just wanted to show you a picture of Humason right here. This is actually at Mount Wilson. He was the one who took the spectra and could measure the redshift, showing the recessional velocity of the galaxy, whereas Hubble measured the distances. So they formed a very effective team and made this one of the great discoveries in all of science. And then what's interesting and almost kind of sad is that cosmology then stagnated for about 20 years with really no significant progress observationally or theoretically. And this is a great quote because it really illustrates the idea of astronomers like in the 20s, 30s, and 40s. And this is, I'm sure many of you have heard of Arthur Eddington, one of the great astronomers of the early 20th century. So he accepted the idea, but he realized how unpalatable it was to others. So he said the theory of the expanding universe in some respects is so preposterous that we naturally hesitate before committing ourselves to it. It contains elements apparently so incredible that I feel almost an indignation that anyone should believe in it except myself. So I think that's actually really revealing of kind of the mindset of astronomers at the time. So the next monumental breakthrough came in the late 1940s, and this was theoretical and not observational. Three physicists, Robert Herman and Ralph Alpher, who were American, and George Gamow, who was a refugee from Russia living in the US, they calculated, they're saying, we take the expanding universe, you play the movie backward and move the galaxies closer and closer and scrunch everything together in an early universe. What would conditions be like if everything's all scrunched together? And they realized that in the first few minutes of the universe's existence, the cosmos had to have been an incredibly hot, dense fireball of elementary particles, and they called this substance Elem, or Elem. I'm not sure it's how it's pronounced. This is kind of this funny photograph they put out. And what they did is then they calculated using, just physics and what they knew about, fusion and subatomic particles at that time, and they calculated the conditions in that fireball, and they determined that what would happen is that the protons and neutrons in this fireball would combine to form atomic nuclei, like what we see down here, into hydrogen and helium. They basically said that what you would get is the universe would be made of 75% hydrogen, 25% helium, and tiny trace elements of a few other elements. Now, what's really amazing and how brilliant this work is this prediction has been spectacularly confirmed by astronomical observations. When astronomers measure the composition of intergalactic gas, that's gas that exists between the galaxies, that has not been processed by stars and enriched in heavier elements, they find, guess what? Whoops, hold on, sorry, whoops. They find 75% hydrogen, 25% helium, and basically nothing else. So this is incredibly powerful evidence supporting the Big Bang Theory. Now, look, about a year later, Alpher and Herman published, this was without Gamow. They kind of split up with him because he was kind of crazy in some ways. But they published one of the most brilliant theoretical papers in the history of science. What they did then is that they said, okay, the early universe was this fireball. It's expanding and cooling as it expands. What would happen to this fireball over the next several 100,000 years as it's cooling and expanding? So they published a paper and said that about 300,000 years after the Big Bang, the fireball would cool to about 5,000 degrees Fahrenheit. That's about 3,000 Celsius. At that point, the universe had, in the early years, the electrons were all just floating freely. It was too hot for them to combine with the hydrogen and helium nuclei to form atoms. But at an age of 300,000 years, when the universe reached this temperature, the electrons could combine with the atomic nuclei, and what that process would do, you'd form atoms. You go from free electrons to atoms, like we see here with hydrogen and helium, and that process, known as recombination, would release a flood of light. And another thing they predicted is that that light that would be released by recombination would radiate uniformly in all directions, and today we could observe it in the microwave portion of the spectrum because of the expansion of the universe would redshift that light. So, not only did they do that, they also predicted the spectrum, the intensity of this background, microwave background light as a function of wavelength. They've said this fireball is going to be in thermal equilibrium, and gases in a thermal equilibrium produce this very characteristic spectrum. So, and I want you to remember this because we're going to get back to this curve in a few minutes. So, they published their paper in the world's most prestigious scientific journal, Nature. So it was right there for scientists all over the world to read their paper. They later published a more detailed paper the following year in the Physical Review, once again read by scientists all over the world. And what's amazing is the technology to detect that microwave background radiation existed at that time, but nobody bothered to look. And this is the most inexplicable thing I'm going to say in my talk today. It's not about the complex science. This paper that they wrote was an absolute work of genius, but it was just forgotten. It was sort of ignored and forgotten for 20 years. And what that did is we had another stagnant period where for 20 years cosmology did not move forward. And tragically, they both lived for many years after this, but neither Alpher or Hermann got the credit they deserved in their lifetime. Now, if you read a modern book about cosmology, they get the credit they deserve, but during their lifetime, they never got the credit they deserved. And around that same time, there was a British physicist named Fred Hoyle. Probably some of you have heard of him. And he coined the name Big Bang as a term of derision during the 1949 BBC radio show. So this theory was actually named kind of in a very derisive way by a British physicist who never even believed and who went to his grave not even accepting the Big Bang theory. He accepted an alternate idea called the steady state universe, once again trying to preserve a static universe by saying that as the universe expands, new matter is constantly being created, keeping the universe in a steady state. So for about 20 years, you had the Big Bang theory, you had the steady state theory, which one is right? Well, 1965 was the next huge monumental breakthrough, as I say here, the year that changed everything. That year, two radio astronomers, Robert Wilson and Arno Penzias, who were working at the Bell Labs in New Jersey, this is the antenna they used, they were trying to figure out what was causing static in radio signals bouncing up and down between the early satellites of the universe. And without even realizing it, they serendipitously discovered the cosmic microwave background predicted by Alpher and Hermann. It took a while before astronomers sort of figured out, including Penzias and Wilson, what it was that they found. And eventually people said, well, wait a minute, there was this paper written 20 years ago. That's what they found. So it took a little while, but once people understood that they had detected this background radiation that had been predicted, it pretty much changed the opinion of most astronomers and physicists. And at that point, the Big Bang theory gained widespread acceptance. Most adherents to the steady state model, except for Hoyle and a few others, they gave up, or didn't give up, but most gave up and accepted the Big Bang. So this was the time that cosmology really became a truly empirical science. Now, if any of you still have a TV with an antenna and tune it between channels, you'll get this static. About 1% of this static is due to the cosmic microwave background. But despite this, even though you can detect it with your television, it's very difficult to study in detail from Earth because we all have all this water vapor and all this stuff going on Earth that helps mask the signal and makes it really, really difficult to study in detail. Now, in 1978, Penzias and Wilson shared the Nobel Prize for Physics, and I would argue that they deserve it. They did very good work. They eliminated all the other possible sources of error. They published their result, and you have to say they made an incredibly important discovery. But a lot of people now say, they were both still alive in 1978, that Alpher and Hermann should have won the Nobel Prize instead. But as I said, for whatever reason, these two great scientists never got the credit they deserved in their lifetime. So I would say that at this point, the Big Bang theory had really started to mature. And I'm just going to kind of give you 6 basic things about the Big Bang. Okay, so the universe basically, according to this theory, came into being at a single moment, what we call the Big Bang. But here's the interesting thing. The theory does not explain how it came into being. That remains a profound mystery. And for people who maybe have more of a, philosophical or religious outlook on nature, there's nothing I would say that rules any of that out. We don't know what caused the bang. The Big Bang Theory says the universe originated in a hot, dense state. The Big Bang is a moment in space, or a moment in time, not a place in space. If someone asks you, where did the Big Bang happen? It happened everywhere because it created space-time. So and another thing is that in every direction you look, galaxies at a given distance are moving away at roughly the same rate. And because astronomers can measure how fast the universe is expanding, they can then infer how long it has been expanding, which tells you the age of the universe. More on that later. So in the 1960s, astronomers started realizing that measuring the Hubble constant, and from now on I'm going to use this symbol here called H0, would be a key to determining the age and evolution of the universe. And if you're curious, the units of measurement are kilometers per second per megaparsec. That's the expansion rate. And if you're curious what a megaparsec is, that is 3.26 million light years. So this Hubble law, which is now known, last year the International Astronomical Union, recognizing Georges Lemaitre's contribution, said we should start calling it the Hubble-Lemaitre law, that there's a proportional relationship between distance and cosmic expansion. So twice the distance is twice the velocity, 3 times the distance equals 3 times the velocity, etc., etc. So in this Hubble, this cosmic expansion, you can measure how fast a galaxy is moving away from us simply by measuring its redshift. But what I said earlier about the Doppler effect does not really apply to the expansion of the universe. And this is, whoops, I keep hitting the wrong button here. This is the really key thing. What's happening as you blow up the balloon, imagine you paint little galaxies on a balloon, you blow the balloon up, the galaxies are all going to be moving away from each other. But what's really happening, it's not really the Doppler effect, it's that space itself is expanding, and that causes the light emitted in these galaxies to be stretched, and that shifts their wavelength that we observe on Earth toward the red end of the spectrum. So that's what's really happening. We're seeing the expansion of space stretching out the wavelength of light from distant galaxies. And you would observe this exact same effect anywhere you're located in the universe. There's no center or preferred location in the universe. Galaxies are not rushing away through space. They are carried away from one another by the expansion of space itself. In other words, new space is constantly being created by the expansion of the universe. You can also think of it, if any of you cook in an oven and you cook a loaf of bread with raisins, the loaf will expand as the loaf heats up. And it's just like what happens with galaxies. The expanding universe causes the raisins to move apart from each other. Now, when measuring galaxy velocity, you have to be a little bit careful because, for example, the Andromeda galaxy is not moving away from our galaxy. It's approaching, and that's because over these short distances, the gravity, the mutual gravity, is stronger, is a bigger effect than the expansion of the universe. So in measuring these recession velocities of galaxies, you have to be careful because this is a cluster of galaxies, the Virgo cluster. All these galaxies are moving around pretty fast from the gravitational attraction of other galaxies in the cluster. So you always have to be careful and account for this effect. Measuring distances, though, is an even harder effect because and this is sort of what Hubble did, is we have what's called trigonometric parallax, where you have Earth maybe in the summer, in the winter. We know the distance from the Earth to the Sun is 93 million miles. So we have a baseline of 186 million miles. And you can look at stars on our own galaxy, and they'll appear to shift if they're close enough during 6 months apart in comparison to background stars. Well, some of those stars are Cepheid variables, so we know their luminosity from the period luminosity relationship. So then using that, you can start moving outward into the universe. So the next rung is, you look at distant galaxies, which are still close enough where you can resolve individual Cepheid variables and monitor their brightening and fading. That's what Hubble did for the Andromeda Galaxy. And I really, because I could spend the rest of this talk talking about this, and I want to get on to more interesting things, but then there are a lot of other distance indicators that, and some of them are listed here on this slide. Don't even worry about the details, but the bottom line is there's other ways that you can then calibrate the Cepheids and extend them to more distant galaxies. And this is called the extragalactic distance ladder. And there has been immense amount of time and observing time and intellectual brain power spent working out the extragalactic distance ladder. So two of the astronomers who did this in the 1960s through the 1980s, who led competing teams, here we have Alan Sandage, who worked at the Carnegie observatories in California, and another astronomer, Gerard de Vaucouleurs, who was French but then moved to the University of Texas. And they then used this method to try to measure the Hubble constant. Well, Sandage's team kept getting values in the low 50s. De Vaucouleurs kept getting values around 100. They couldn't figure out how to resolve that discrepancy, basically a factor of 2 discrepancy. And science isn't supposed to be about personal animosity. It's like you follow the data, but science is conducted by human beings with all their foibles. So this controversy lingered for years and years, and it degenerated to the point where these two men absolutely hated each other's guts. Another thing that was going on that was not maybe fully appreciated either in the whoops, I keep hitting the wrong button. In the 1930s, Fritz Zwicker, and then I would say more convincingly in the 1970s, Vera Rubin, working with her colleague Kent Ford, discovered that most of the universe's gravitating matter does not radiate or absorb light. And we now know that this dark matter outweighs our familiar atomic matter by about 5.5 to 1 in terms of its mass. Zwicky made his conclusion by noting that the motions of galaxies within clusters, the galaxies were moving too fast for the cluster to hold together based on the estimate of the amount of mass from the light of their stars and gas. And he said there had to be more matter there that we can't see, and he was right. And then Vera Rubin did it a completely different way. She looked at a lot of different spiral galaxies, and what she observed is the velocity of the stars should fall off as you get farther and farther from the center of the galaxy, just like Pluto goes around the sun a lot slower than Mercury. But what she found in most galaxies, they would keep speeding up, or in some galaxies it would be a flat line. And like, how could that be? Well, if you model a galaxy as having your bulge in a disk surrounded by a vast halo of dark matter, then you can account for Vera Rubin's observations. Another huge breakthrough, and this gets really complicated, this is difficult to explain and understand, came in the late 1970s. Two Soviet physicists, Alexei Starobinsky and Andrei Linde. Linde later moved to the US and he still works at Stanford University in California. And then independently, Alan Guth, who's now at MIT. I've met him a bunch of times. He is a really, really nice guy, and brilliant, and a really nice guy. I think the world of him. They came up with the idea of cosmic inflation, which resolves some of the problems left over from the Big Bang. I'm only going to have time to give you one problem, is by that time it was becoming pretty clear that the universe's geometry is spatially flat on large scales. Well, why should that be? Inflation, as I'll explain in a minute, explains that. When I say spatially flat, it means if you could create a triangle and extend it over millions of light years, an equilateral triangle, the angles would still add up to 270 degrees. Or if you took two parallel light beams and just shown them, the two light beams over millions and millions of light years would remain parallel. There's other types of universes that could have existed. We could live in what's called a closed universe, where it would be more like a sphere, or an open universe shaped more like a saddle. But all the observations to date very strongly suggest that we live in a flat universe. And what inflation does, it would be like taking the Earth and expanding it out millions of times its size. You know, the Earth would appear flat. I mean, it actually does, and that's why it took a long time for them to prove that the world is round. But imagine if the Earth was like billions of times larger, it would be effectively flat from anywhere where you would observe on the surface. So inflation is this idea that in the very early universe, like the first 10 to the minus 35 of a second, the universe went through this incredible growth spurt where it expanded at this exponential rate, doubling in size at least 85 times in a tiny fraction of a second. But I also want to point out there are many different versions of this theory. So this slide just kind of compares the standard model. You get kind of a smooth expansion, inflation. You start from a smaller seed. You get this sudden burst of expansion, very short-lived, but a phenomenal expansion rate. And then the universe settles back down into the standard model. So the idea with inflation is at the end of inflation, the energy that drove the inflation, then after this inflation ended, transformed itself into the particles and radiation that we see in the universe today. Now, if inflation is correct, and it probably is, although it's not proven beyond doubt, the observable universe that we see to the greatest distances is only a tiny part of the entire universe. This early expansion created a universe that's even bigger than we could ever hope to observe. Another exotic possibility, this gets a little more speculative, but it's not totally crazy, because very smart people believe this, is that this inflating space-time created this never-ending process where it kept producing new universes. So if this idea is correct, we live in a multiverse of just enormous numbers of universes, many of which may have physical laws totally different from our own. But this, once again, this is far from proven. We don't have any observations that rule this out. There is some basis in fundamental physics that this might be true. But personally, I wouldn't put a lot of money on it, but I wouldn't bet a lot of money against it either. Another big breakthrough came in the late 1980s, and I remember I was like really getting interested in astronomy at this point. And this was really, some of you might remember, because when this came out, this was big, big news. Two astronomers working together at Harvard, Margaret Geller and John Huckra. And by the way, when I worked at Sky and Tel, we would play Harvard in softball. So I played softball against John Huckra. He was pretty good too. But they created these three-dimensional maps where they mapped the distances of galaxies, and they realized how non-uniform the universe actually is. If you plot galaxies, you know, their sky coordinates versus distance, they called this like this stick man but they found that the galaxies kind of form these long filaments, and inside these filaments are these immense voids with very, very low density of matter. So this discovery showed that this hot gas, going back to the time of recombination, remember the Alpher and Herman paper, the gas must have been nearly but not perfectly uniform, because we now know that the universe is a little bit clumpy in its structure. So then, and this is when I was really getting into astronomy. This was a huge discovery, and I got really excited about this, and justifiably so. This actually made like the cover of Time magazine. Probably many of you remember this. NASA had a small satellite called COBE for Cosmic Background Explorer, and it measured the CMB spectrum. And remember that curve I showed you a few minutes ago? That's the curve, the predictions from Alpher and Herman. The data points with the error bars from COBE are these red dots on the green curve. I would submit, and I think all of you in this room would agree, that's a pretty spectacular match between theory and observation. What this curve proved is that the universe must have originated from a hot, dense gas in thermal equilibrium, i.e. the Big Bang. Then another major discovery from COBE is it found very tiny temperature variations in the microwave background, meaning you look in one direction of the sky, the temperature is this. You look in a different direction of the sky, and the temperature might be slightly hotter or slightly cooler. And when I say slight, I mean slight by about 1 part in 10,000. Tiny little variations in temperature. They were able to determine that the CMB was released about 380,000 years after the Big Bang. So Alpher and Herman were a little bit off, but not by much. Their paper said about 300,000 years. Now if you look, this is actually a movie, the only movie in my presentation. What we think happened, in fact this is probably right, is these quantum fluctuations, these little fluctuations of particles popping in and out of existence, predicted by Einstein in his cosmological constant, that the quantum fluctuations during this period of rapid cosmic expansion, inflation, seeded the structure of the universe. These quantum fluctuations made the universe, some areas of the universe, slightly higher in density and some slightly lower in density. Gravity then over billions of years worked its magic, formed clusters of galaxies, and other areas were less dense, the voids, and that would show up in these temperature variations in the microwave background that COBE observed. And what happened is most popular articles about the microwave background really don't give this explanation, but this is really important. So imagine you have this early universe. It's still a very, you've got billions of galaxies of matter crammed into a very small space, very hot, very dense gas. Well, sound waves are going to be propagating through this material, just like sound waves propagating underwater. And the sound waves are going to cause matter to bunch up a little bit more on average in some places than others. And it's the action of these sound waves that created these hot and cold spots in the microwave background. And the exact manner in which they would do it would, whoops, okay, I'm nearing the end here, would depend on the exact match of atomic matter, dark matter, and what we now call dark energy. The COBE science team leaders, John Mather and George Smoot, shared the 2006 Nobel Prize in Physics for these discoveries. But if you read Mather's book and talk to other scientists, and I agree with him, Mather certainly deserved it. The other guy, Smoot, was an opportunist. He broke the agreement of the team, made the announcement when they were supposed to make it as a team. but he held his own press conference so he'd get all the fame and credit, and the rest of the team was absolutely furious at him. He later was forced to write an apology. The other two scientists who should have shared the prize with Mather were Ned Wright on the left and Nancy Beaujess on the right. I'm going to move forward here, so I just want to go for another 5 minutes or so. 1998 was another monumental discovery. I bet you many of you remember this, when two different teams, one led by Brian Schmidt and Adam Rees, left and center, another group led by Saul Perlmutter on the right, discovered that the universe's expansion rate is accelerating, and that was due to what we now call dark energy. They made this discovery by monitoring what we call type 1a supernovae, which are much brighter than Cepheids. They're caused by white dwarf stars that accumulate matter from a companion star, eventually become unstable and blow up in gargantuan explosions that can be seen at billions of light years distance. 2002, there was a Hubble team led by Wendy Friedman and her husband Barry Medor. They measured a Hubble constant of 72. Notice it's sort of right in between the Sandage and de Vaucouleurs groups. I'm going to have to skip by here. 2008, another NASA satellite called the Wilkinson Microwave Anisotropy Probe, or WMAP, made a much higher resolution map of these temperature variations that were seen by COBE, but now we're seeing them at a much finer, much higher spatial resolution. By analyzing the statistical patterns of these hot and cold spots, they're able to determine that the match is a perfect match for inflation and a flat universe, and they can calculate a cosmic age of 13.7 billion years. By plugging this into their model, which they called lambda CDM, they get a universe that's 74% dark energy, 22% dark matter, and 4% atomic matter.
Wow.
Yep.
You go another 10 minutes.
Okay, 10 minutes. Okay, I'll slow down a little bit. Okay, I just don't want to go too long. Now, if any of you think this is crazy, here's why I think this lambda CDM model, lambda is for the cosmological constant, CDM stands for cold dark matter, meaning that the dark matter consists of heavy elementary particles that don't emit or radiate light or absorb light. If you plug this mixture, this cosmic recipe, into a computer and then plug in the equations of general relativity and say, okay, this is what the universe was like at the time of the microwave background, and the universe has this much dark energy, this much dark matter, this much familiar matter, and you let it expand at the rate that we observe, and you just let the universe evolve inside a computer, this is kind of what you see happening. And this is the prediction of what the universe would look like today. This is a large international collaboration using these giant supercomputers to model the large-scale structure of the universe today as predicted by the simulation. Okay, then you want to compare that to what does the real universe look like. So that work that Geller and Huckra I talked about a few minutes ago with our modern telescopes and the better detectors, you can now extend that survey out to much larger and greater distances. And this is what you find. This was a study done in Australia, and then this is a study done in the United States. And if you compare these maps of the real structure of the universe to the predicted structure and kind of do a statistical comparison, it's an exact match, okay? I mean, the model, this lambda CDM model, passes the test with flying colors. So it might be partially crazy, but it's not totally crazy. The next big step came in 2013. There was a European group that put together a satellite called Planck, that made an even more detailed map of the microwave background. Here we can compare COBE's cruder resolution, WMAP better resolution, and Planck has the best resolution of all. And when they did all the calculations, measured the sizes of these cold and hot spots, which once again were produced by these acoustic waves rattling through the very, very early universe, and the exact nature of how those waves would propagate and how they would cause these spots to form would depend on the exact recipe of familiar matter, and dark energy. And they just slightly refined the results from WMAP. Not really fundamentally changing it in any major way, but kind of just tweaking the numbers a little bit. And this is where it gets really interesting. They're predicting a Hubble constant of 67.4, and they're now saying that the universe is 13.8 billion years old. Just slightly different from the WMAP results, but basically consistent. And this is really what my article's about, is there's a tension going on because groups that use this distance ladder method that I talked about a few minutes ago, they're getting Hubble constants of about 73. Remember, the Planck team is saying 67. So these groups are now using better tools than what was available to Wendy Friedman and her key project team back 15, 20 years ago. And since I am running out of time, just quickly, they have more distance indicators to calibrate the Cepheid distances. One thing, they have better distances now to the Cepheids and our own Milky Way galaxy, thanks to the European Gaia satellite and new cameras on Hubble. So the end result is that these new Hubble constant measurements are more accurate and precise than the earlier measurements. So the SHOES team, led by Adam Rees, one of the Nobel Prize winners for discovering cosmic acceleration, his team is now getting a Hubble constant of 73.5 plus or minus 2.2%. I want to make it clear, this is in perfect agreement with Wendy Friedman's result with the Hubble Key Project, but notice with these new methods that were unavailable at the time to her team, the error bars, the range of uncertainty has gotten a lot smaller. There's another team led by Chris Burns at Caltech. Actually, Wendy Friedman at one point was a member of this group. He's getting almost the exact same result that Adam Rees was getting. Within the range of uncertainties, their measurements agree. I mean, they're not fighting with each other because they're basically getting the exact same result. Then there's another, this is a huge international group, and this is a horrible acronym called Holy Cow, but they're using a totally different method where they're looking at quasars that flicker in intensity, and these are quasars that are gravitationally lensed by foreground galaxies, and in a very complex geometrical arrangement, they can also measure the Hubble constant, and voila, they're getting 72.3 plus or minus 3%. And I interviewed all these scientists on the phone. They're very happy. They're all getting the same result. There's no argument here because they're getting the same result, but they're not getting the same result as what you get from studying the CMB. And I should point out the WMAP gives you larger error bars, but it basically agrees with Planck. So what we have now is we have a discrepancy where the teams that, and once again, it's not really measuring the Hubble constant, but predicting the Hubble constant from the microwave background gives you 67. The other, using the more traditional methods, are giving you measurements of around 72 or 73, and you'll notice that their ranges of uncertainty are called the error bars, are no longer overlapping. Now, I interviewed some CMB people. I interviewed, Adam Rees and, Burns and Sherry Suyu. This is not a personal disagreement. It's very professional and proper, the current discussion. It's like, what the heck is going on here? Because these measurements should agree, and they don't. And so that's what's interesting, that everybody has confidence that the measurements are being done correctly, but these different methods are giving different Hubble constants. And as Adam Rees said, there's less than a 0.01% chance of this kind of difference occurring just by chance. So, I think what's going on, there's something missing in our model of the universe. There's something important. It's not like our model of the universe is way off, because 67 and 73 aren't that far apart, and the lambda CDM, this model of the universe, is very consistent with astronomical observation. The problem with lambda CDM is it works really, really well, but there's a lot of unknown physics. What the heck is dark matter? It's 26% or 27% of the total energy in the universe, but we haven't detected it. We don't know what it is. Okay, even worse, what is dark energy that's driving accelerated cosmic expansion? That's 68.3% of the universe's total energy. There's lots of different ideas of what dark energy is. It might be this vacuum energy, this cosmological constant that Einstein predicted all the way back in relativity, but it could also be some kind of dynamical field that changes over time. That's known as quintessence, or it could be something else. We really don't know. There's a bunch of observations that will hopefully in the next 5-10 years, reconcile all of these measurements by looking at even more distant supernovae. We can get a better handle on how the cosmic expansion rate has changed over the history of the universe. It turns out you can get an independent measurement of the microwave background, not from the hot and cold spots, but by looking at the polarization of the photons in the microwave background. Very, very difficult measurement, but that work is being done right now. These sound waves in the early universe, I talked about how they would cause matter to bunch up more in some places than others. That's why we have the lumpy, soapy universe. Astronomers are trying to directly measure what are called baryon acoustic oscillations, or BAOs, by looking at how galaxies are spaced. There should be a preferential spacing that changes over time as the universe expands. Very incredibly difficult thing to measure, because you have to measure this at nearby but also huge distances. But once we have better measurements, that should give us a better handle on cosmic expansion. There's also gravitational waves. We've detected gravitational waves from one set of neutron star mergers. When we detect more of them, and LIGO's just been turned on, they can see gravitational waves events at much larger distances. Like probably 10 years from now, they'll have many dozens of events. They can use those as standard sirens, not standard candles, but standard sirens. And the LIGO scientists are very confident they'll be able to nail the Hubble constant to within 1%. So I want to just conclude by saying the Big Bang Theory, adding inflation, and the lambda CDM is not proven science, but it's consistent with all astronomical observations. I think, and I think I've been able to demonstrate to you tonight, it has enormous predictive power. It predicted many discoveries before they were made. That's the hallmark of good science. And I would just say right now it's the best theory we have right now for the early evolution of the universe. My final slide is I'm also hoping, and I include a quote at the end of my Astronomy magazine article, is a resolution to this mystery about these different versions of the Hubble constant might shed something really important on dark energy, which once again is, about 2/3 of the energy in the universe, and it's really dark energy that controls the universe's ultimate fate. If the dark energy is some kind of dynamical field, there's still a hope that it'll change as the universe evolves, maybe cause the universe to collapse back upon itself, or maybe even cause physical laws to change. That's called a big crunch. If the dark energy is in fact what we think it is, the universe will just continue expanding forever. The stars will eventually die out. Even black holes will eventually radiate away all of their mass, and the universe will just be a vast sea of essentially nothing. Or if the dark energy is some dynamical force that gets more and more powerful, we're in for a very unpleasant long-term future called the Big Rip. Well, the dark energy will just eventually tear everything apart, you know, including atomic nuclei, subatomic particles, and it'll just tear everything apart, and the universe will once again be a vast sea of essentially nothingness. So I'm hoping in my lifetime, we'll resolve this problem, so at least I know what the long-term future of the universe will be. Thank you. So I'm sure there are questions. And I went through things really fast, so feel free to ask me for more details. Yes?
Well, I am curious, so after maybe 100 years of astrophotography on record, is there actually any visual proof of the expansion? And if not, how much time do you think has to go by before someone can actually say, oh look, such and such a galaxy is further away now than this plate we took in the early 1900s or something?
Great question. Could everybody hear it okay, or should I repeat the question? Could everybody, if you couldn't hear it okay, just
repeat it again.
okay. He's basically saying, how long would it take before we would have photographic evidence, you know, that the galaxies are getting farther and farther apart? You know, because we have photographs now, you know, like the Andromeda Galaxy, going back well over 100 years. That's a very good question. Now, when we talk about these units of the expansion of the universe, it seems very fast, but on the scale of a human lifetime, it's actually pathetically slow. So the reality is we would probably need to be around for like millions of years, because I think what you're getting at is like if a galaxy is moving away from us, over time it gets fainter and fainter. And that is true, but because of the expansion on a human life scale, even like multiple generations of humans is not fast enough that you would really see that unless we could be around like for millions of years. But you're right, if we could live and take these measurements over or if the dinosaurs were taking pictures, you would probably see that things are changing a little bit over time. But you need to be alive for a very... Unfortunately, the dinosaurs, as far as we know, never built telescopes. Any others? Yeah, let's see, I'll go Lane and then next door.
Did Edwin Hubble ever compute the Hubble constant for himself?
Yeah, he really did not, because, and by the way, I brought 3 books, and this is a good time to introduce them. This is a great history book called The Day We Found the Universe, written by a friend of mine, a science writer named Marcia Bartusiak. And then this is a great book where you really read about how much DeValcouleurs and Sandage and their whole teams hated each other, called Lonely Hearts of the Cosmos by Dennis Overmy. And then a book I just read to help prepare this talk is by John Mather, the lead scientist for COBE, who won the Nobel Prize, called The Very First Light. In this book, it really goes into depth about Hubble. Now, Hubble was, no doubt about it, he's one of the greatest scientists, not just astronomer, but one of the greatest scientists who ever lived. But he was very much an observer and not someone who was really prone to stick his neck out in interpreting his own data, because he had this terrible fear that if he just published his data He was a very careful, great observer. He'd be right. As soon as you stick your neck out, and you start interpreting your data, then you have a possibility you're wrong. So he really never, and sort of astounding that his second great discovery, he never fully accepted the implications in his lifetime. If he had lived, he died fairly young. I think he died in his late 40s or 50s. If he had lived long enough to see the discovery of the microwave background, I think then he would have said, okay, I'll believe the universe is expanding. And at that point he's like, okay, yes, measuring the Hubble constant is really, really important, but he never could fully buy into the idea that the universe is expanding, and therefore he wasn't really interested in measuring or trying to ascertain the expansion rate of the universe. And I'm not saying, I don't blame him. I mean, that was just kind of the way he did his science. And given his two monumental achievements in his career, it's kind of hard to say that he was wrong or wasn't. I can't really blame him for that. And after all, we've named the Hubble Space Telescope after him, which was very fitting that we named it after him. But he never really was interested in trying to measure a Hubble constant, even though it would come to be named after him, which is kind of ironic. Yes, another question.
I'm thinking back to your pictures about the geometry of the universe, and you said it could have been a sphere, could have been more of a saddle, but we think it's more just flat and straight out. Are you saying that what we observe is flat and it could be one of those other universes? Or we think the entire universe has more of the flat geometry just in its entirety?
Yeah, that's a great question. And here's the thing, of course, on local scales, the universe is not flat. And I'm glad you asked that question, because when I say it's spatially flat, and I do say on very large scales, what I mean is over billions of light years, the universe is spatially flat. And there's, and I'm not an expert on this, but there's different effects that you would observe if the universe was a closed universe or an open universe. The real clincher, though, that the universe is spatially or geometrically flat comes from WMAP and Planck, that when you model with this lambda CDM model, and you model what we know about dark matter, dark energy, and normal matter, and then you model how that would show up in the CMB, this spatially flat model, which includes inflation, it gives you, and this was all predicted years before these satellites were launched. And they, for example, the average, most powerful size in the spectrum of the microwave background are with these spots, these hot and cold spots about 1 degree across. That's like the size that gives you the most power in the spectrum. And that is the prediction of a flat universe. So in other words, if you would have a non-flat universe, like a little bit less than 1 or a little bit greater than 1, then what would happen is that those spots would get larger or smaller, and you would get a different statistical pattern in the microwave background. Now, if this was a post facto discovery, okay, I'm not sure I believe it, but when Guth and these Soviets came up with inflation in the late 70s and early 80s, within a few years, these predictions, these physicists were predicting the physics of the early universe and predicting the different shape, the different patterns you'd see in the microwave background long before they had satellites that could actually measure it. So that's the most powerful evidence that we live in a spatially flat universe. The other thing, too, is that if this is something that one of the team members I quote in my article, Gary Hinshaw, said, if, let's say, the universe was not flat, but slightly spherical or saddle, the whole universe becomes dynamically unstable. So the fact that the universe appears to be stable is very good evidence that it's flat, that it's spatially flat over enormous distances. Time for one more, or do you think that's about it? I know we're library closes in a few minutes.
One more.
Yes, over here.
You gave a very good example of a characteristic of dark matter. Is there a comparable characteristic that is easy to understand as far as dark energy is concerned?
Yeah, that's the thing. Dark energy is such a weird thing. There's people say, well, we don't know what dark energy is. Well, the thing is, there's been like hundreds of papers that have been predicted with different predictions of what dark energy actually could be. So I would say maybe one of these papers is right, but we don't know which one. I think the best idea, the one that most scientists think is the most likely explanation, is this idea from Einstein, that it's what's called the cosmological constant. And what this is that we know that there's no such thing as empty space. That what we think of as empty space, there's actual constant, there's energy in that empty space that produces particles that then appear and disappear in a fraction of a second. This was actually predicted in the early 1900s with quantum mechanics, and it's been proven to be true experimentally. So we know that empty space has energy, but then you try to calculate what that does to the universe on a large scale. You can fine-tune it to give you the current acceleration rate that we observe, but you have to really fine-tune it. It makes scientists very uncomfortable because it works, but it doesn't mean that it's right. And that the energy, you can calculate lots of different values for how that dark energy would affect cosmic expansion. If the dark energy is too strong, it blows the universe apart. If it's not strong enough, then the early universe would have collapsed back upon itself. So you have to kind of fine-tune it to give us the universe that we observe today. So, I wish I could give you a better answer. We really don't know what dark energy is. That's the best guess. But I just turned 56 last week. I think in my lifetime we'll find out what dark matter is. I don't think in my lifetime we'll nail the answer of what dark energy is. We really don't know. It's a profound mystery, and it's 2/3 of the energy of the universe. So we don't know what 2/3 of the energy of the universe is. And when you add dark matter, we're up to about 95% of the energy of the universe. So we don't know what 95% of the energy in the universe is. And yet, if you make certain assumptions about what it is, the model, the cosmological model, fits observations really beautifully. So it's a mystery. I think it's a mystery why we know as much as we do when we don't know what 95% of the universe is, if that makes sense.
I would put it another way. I think it's terrific that at least we have a pretty good idea of what we don't know.
Yeah, that's true.
Which is mostly everything.
Yeah, that's a great point. If you don't know, like, think how dumb we were before we didn't know about dark matter and dark energy. I mean, now, like, at least we now know that it exists, and we can design experiments and observations to try to detect it. So that's progress. And even though we don't know what it is, you can model its effects on the universe and come up with a model that really explains very cleanly and accurately the universe we actually observe. So I find that kind of incongruous, that we can still model the universe without knowing what 95% of it is made of. Isn't that kind of crazy?
Well, thank you all for coming. I hope you had a good evening.
Yeah, thanks for coming. Thank you.